Okay, the lecture everybody's been waiting for, the digital abstraction. And we're going to talk about making concrete canoes. Wait, no, that can't be correct. This is double E. Oh, we're going to talk about making bits concrete. We're going to ask a question, what makes a good bit? And we're going to get bits under contract, which is what's going to allow us to do what we need to do with them. Oh, by the way, this is one of Lamar's uh, concrete canoes. Let's talk about the concrete encoding of information. We've already discussed encoding information using bits, but where do they come from? Where do these bits, do we just write them on paper, or do they have some reality? Well, if we're going to design a machine that manipulates information, and let me pause here for a minute. This is sort of what we're about with all this. We're digital logic design. Back in the day, I've already told you some of the history of it, was more constrained not so much to designing a machine as it was to designing the very simple things. And we'll see what those simple things are later. But now we have the ability, because of the digital abstraction and the place that it has gone to go all the way to the design of a computing machine, a computing engine, a computer. And so if we're going to design a machine that manipulates information, which is what a computer is, how should that information be physically encoded? And so let's ask, what makes a good bit? First, they're cheap, or they need to be cheap, because we're going to use lots of bits. Megabit, uh, terabit, gigabit. We also want them to be stable, in other words, reliable and repeatable. And they should have some ease of manipulation. In other words, we need to be able to access them. We want to transform them. We want to combine them. We want to transmit them. And we also want to store them. Because remember, we've looked at encoding, and those bits represent information. And we already access information by going to the library or a bookstore. We transform information by finding something out and then texting it to a friend of ours. We combine information. We might write a report where we take information from multiple sources. We transmit. I just said we could text someone. I just was over at Starbucks and saw so and so. And lastly, we store information. We take pictures on our phone, let's say, and then store them in memory, and then later do those other things. So this is what we're talking about, and we want bits that are easy to manipulate. This is one of the examples from Steve Ward's original materials at MIT, and this is a little history thing. He said to his friend, "If the British march by land or sea from the town tonight, hang a lantern aloft in the belfry arch of the North Church Tower as a signal light. One if by land and two if by sea." Of course, that's the Paul Revere thing. And so the lantern was a bit, was a bit of information, and it was used to signal that the British are coming. It turns out that I think that historically none of this really happened, but don't hold me to that. I like this one, which is mine, which is closer to home. A blood-red flag flew from the steeple of the parish church in San Antonio, Texas. It was hoisted there by soldiers of the Army of Mexico's dictator, General Antonio Lopez de Santa Anna, on February 23, 1836. The meaning of this flag was clear to the 186 Americans, or Texicans, basically, at that time, holed up in the Alamo. The flag stood for no quarter. Unless the Americans surrendered, they would be slain to the last man. So, sort of a depressing signal, but nevertheless, that flag, like the lantern, was a bit of information, like telling them this is what's going to happen to you. So, I'll just leave this slide by saying, remember the Alamo. Okay, let's talk about substrates for computation. We can build upon almost any physical phenomenon. We just mentioned lanterns and flags. We could create an information processing system with dominoes. And that's what that example is there over there in the upper right corner. That's an exclusive or one-bit adder. Now, you probably don't even know what that means. It sounds like Klingon at this stage. Later on, we're going to look at exclusive OR gates, and we're going to see that an exclusive OR could be used to make a one-bit adder, or basically is a one-bit adder. In other words, it can add 2 bits together. But anyway, you can go on the web. There's a simulation that shows how that works. You can use engraved stone tablets, to store information, and then also use them to compute, believe it or not. Billiard balls, see wiki. So you want to go to Wikipedia and do billiard balls computing with billiard balls, and you'll see that can also be used. There's all kinds of crazy ways to manipulate information and represent bits. These last two, like the screen bean says, E. coli. E. coli, you may know, is a bacteria. It causes people to get sick. We have it in the human gut. It behaves itself because it's under control. But the molecular biologists who were involved in what's called synthetic biology use E. coli to create certain complex molecules and what they call designer proteins. So they make E. coli generate these things. And so they treat E. coli like a transformation machine. And it also involves the information, of course, of DNA, which is shown there over on the right-hand side. We're going to talk a little bit more about that. So that's on the biology end, and then we can shift to the physics end, the non-EE physics end, and look at the notion of the polarization of a proton. And that's what's happening down there in that little diagram. You have, I say a proton, I mean a photon. You got a photon A, a photon B, they're interacting with mirrors, and based on their polarization, will determine whether or not you get an AND operation, not and get different logic results based on photon polarizations. So if you can polarize the photons in a particular bit pattern and run them through a mirror system where they interact, you can get various results. And that's right on the edge of quantum computing. And that's as far as I'm going to go with quantum computing. And frankly, the big one is our own DNA, or the DNA of life and all living organisms. Here we've got an mRNA, a messenger RNA, and it's basically sort of one strand of the DNA double strand. So as you see, you've got this sort of open staircase as opposed to the closed if we had the double strand DNA. And basically, you have these 4 bases, G, C, U, A, and those code, those are a code and encoding for the creation of protons. Proteins. I'm having a rough time this morning. So, and we'll come back to this. All right. That's all a lot of fun, but since we're double E's, let's stick with things we know about. We know about voltages, phase, currents, frequency. That's what we work with. This semester, for this course, we're going to use voltages to encode information. But the best choice depends on the intended application. So you may want to encode with one of these other things. It just depends on what you're working with. What are the pros of using voltage? Well, first of all, it's very easy to generate them. It's easy to detect them, voltages. There's lots of engineering knowledge. There's a large storehouse of information on voltages. And you're going to spend, what? This course we're going to work with voltages. Intro to EE, Circuits 1, Circuits 2, Signals and Systems, Electronics 1. Electronics gets into current a lot. There's a lot of current going on in electronics if you're working with bipolar junction transistors. But anyway, and then you're going to get the fundamentals of power and do lots of voltage again. But now in power, you're going to be phase, frequencies are going to come into play, and currents. Anyway, my point is lots of information. And potentially low power in the steady state, possibly zero power, which means it's efficient. What are the problems with voltages? Well, easily affected by the environment. So voltage is very noise susceptible. We can ask, is DC connectivity required? In other words, everything has to be connected, whereas with frequencies and things of that sort, you don't have to have them connected. You can, with sinusoidal voltages, for example, and we're looking at DC. So we're saying, do we have to have DC? And the answer is pretty much yes at this point. And R and C effects slow things down. That's resistance and capacitance. If you didn't see that when you first looked at that, start thinking R, resistance, C, capacitance. That's our bread and butter along with inductance. But anyway, RC effects slow things down. You know, when you have an RC network, it has this exponential, the capacitor charges exponentially. That slows the voltage down. If you have parasitic capacitances, which is capacitances that occur as a nature of the hardware, that's going to give you problems with voltages. But we can work around all that. Now let's take a short segue and talk about representing information with voltage. Now remember, we talked about black and white television back when we were talking about encoding. And let's say we want to represent each point on a black and white picture, just a single frame from a black and white television, a picture, or a black and white picture, a photograph, black and white photograph. Everybody knows what that is. There's an example there. Each point, X, Y, on the picture. Now, what are those points called? Well, you already know pixels. Down there at the bottom. Those points are called pixels. Pixel means picture element. Okay, so we're going to say if the pixel value at that point on the picture is equal to, on the screen or whatever, is equal to 0 volts. So now we're representing a pixel by voltage. If it represents 0 volts, we're going to call that black. If it's 1 volt, we're going to call that white. Okay, and that black and that white depend on the capability of the medium. For instance, you're looking at this on a screen, and how black the screen can make a pixel depends on the quality of the screen. And in fact, blackness, the deep depth of the blackness costs you. If you go to Best Buy and start looking at televisions, some of the televisions say, we have the blackest blacks in the industry, and that's going to cost you. Likewise, the white is the brightest the pixel can be, and to get that really bright white pixel is going to cost you. Now we're going to talk about a range in between the black and the white. And let's say we have 0.37 volts. Well, we're going to call that 37% gray. So it's sort of dark, but it's not black. And then if we have 0.5 volts, that's going to be 50% gray. That's going to be a gray that's in between the black and the white, and etc. So depending on what those various values of voltage. So the representation of a picture, we're going to scan points in some prescribed raster order and generate a voltage waveform. So if we look at this black and white picture, and by the way, does anybody recognize that? That's from a movie 2001, A Space Odyssey. And this is the two astronauts on the spaceship, and they're sitting in a pod, and I think they're trying to keep the computer, this evil AI computer, HAL, from hearing what they're talking about. Later they find out. I don't want to make a spoiler for any of us, but by now, if you haven't seen that movie, good grief, it turns out the computer can read lips. So the raster is that pattern of blue lines that I've got on there. And you start up in the upper left-hand corner and scan across. And so if you can imagine looking at the first line of pixels, which is that first row, then the next row, and of course that makes a continuous set of pixels, and we do that in time, and that's called a raster scan. And that'll generate a voltage waveform. And so we can sort of at this point ask how much information is at each pixel. And it's going to be dictated by those voltage values. We can also talk about probabilities, like we did with Huffman coding. And now we've got at each pixel, let's say we have a byte of information. So we have 256 values. 0 is black and 255 is white, and so on. So hold that thought about the black and white TV. Now let's talk about a random number generator. You're going to recognize this immediately as C code. And remember, if you had only Java, Java is like C. You need to go and get familiar with C. You don't have to become a C programmer, but you have to become familiar with it. And there's some materials on this website, on the course website, to help you either refresh yourself about C or to understand C and be able to read, for instance, this program. So there we've got an include file up at the top. We've got a static unsigned integer next, and we're going to make it equal to 1. So static, of course, means that it's going to stick around, and we're going to have a location in memory we'll refer to as next that equals a 1. We're going to have 3 functions, rand underscore r, and then rand, and then srand. So rand underscore r is going to take a variable seed, an unsigned int, and seed, let's see, unsigned int seed. And we're going to make seed, and of course the star seed means that it's the address of seed. We're going to make seed equal to whatever the prior value of seed was. We're going to assign seed. The prior value of seed times that big long number, okay, that huge number, plus 1, 2, 3, 4, 5. And then we're going to return, we call integer, when we call rand underscore r, we're going to return that new value of seed modulo rand max plus 1. So whatever rand max is, and that's going to be in lib payload, and that's going to be dependent on the operating system. And so we're going to modulo seed by whatever the largest, so whatever seed comes out to be, when we add that, when we multiply by the big number and we add the 1, 2, 3, 4, 5, whatever that big number is, we're going to modulo it to the max, and so that'll hold it to that size and do the multiple of it. So when we call rand, we're just going to call rand underscore r with the address of next. And of course, next is equal to seed. So what's all this manipulation do? It generates a random number. It generates a random number from 0 up to whatever rand max is. Okay, we can set that actually if we want. So we could say rand max is equal to 32, so we'll get a random number between 0 and 32. And so we can generate whatever kind of random numbers we want. Okay, back to the television set. So here's a TV, a black and white TV, and this is what they look like. They have those two knobs. Well, actually, could have been a color TV. But here's a black and white TV, and you hear that shh sound. It's actually my computer heating up, but it does sound like that noise, right? And what we've got is noise on this television screen. And what you're able to see, because I've made it that way for clarity, is the pixelation of the picture. So now if you consider that raster, that line of little black and white squares along the top, and then the next line and the next line, that's that signal. And that signal is those different gray values. And now in this case, it's fairly correlated in time, so it doesn't change a lot. But this is what I have called the infinite image window. And in 2005, I had a grad student, and he graduated, obviously 10 years ago. His name was Venkata Prabhala, and for his thesis, I had him analyze the notion of the infinite image window. What do we mean by the notion of the infinite image window? Well, the reality is that if you had a random number generator, looking at the random values of each pixel and causing each pixel to change randomly ad infinitum, eventually you would begin to observe interesting things happen. While you were looking at this image, oh, and here it is again, I had to change it a little bit. While you're looking at this image, let's say you froze the screen. And now you've got this basically image of just noise. It looks like a texture. It looks like it might be something like a pattern, but it's noise. Okay, each pixel, we called our random number generator and we pulled out a random number. Now let's say that the gray values, in other words, the variation on the gray on this, we'll call this the infinite image window TV. Each pixel, remember, can go from 0 to 1 volt. And let's say we divide up from 0, we use 256. So we go from 0 to 1 to 2 to 3 up to 255. We can represent 0 to 255, those gray values. Remember, 0 is black, 255 is white, 126 would be 50%, so it would be half gray. So let's say we call our random number generator and we tell it to give us random numbers between 0 and 255. And so each pixel then has a random number. So, and let's say we have a little button, and each time we press the button, it gives us a new random sequence, on two-dimensional random sequence on this screen. Okay, so if we sort of hit the button, and every time we hit the button, we get a change, we might start to see things. Now, this pattern that we see here could be generated by the random generator. But you see, it's starting to become correlated. In other words, we're starting to see sort of blobs in there. We're starting to see lines appear. Uh, it doesn't really, it's still like just nothing. But it does appear to have some organization, some structure. And in fact, this even evokes notions of self-organization in digital systems. But that's that's a subject for graduate school. But anyway, so we hit the button again, and in that noise, we might see a face. And this face is like almost like a computer-generated graphic face. It's not a real human face, but it's a face. We recognize it as a face in that noise. If we hit the button again, we might see an animal. And now this isn't a graphic. This could be a noisy photograph of a leopard. And we hit the button again. All of a sudden now, these are people. And these people could be from a sitcom in the 50s. In fact, I think that's what that they're from. But they're not in a scene. They're superimposed on noise. So the combinations that could occur are infinite. We hit the button again, and now we see an actual, it looks like a photograph. In fact, this could be a photograph of you as a baby, and your parents were goofing around and stuck a headset on you. We hit it again, and now we could see a photograph of something that happened in history. Obviously, Martin Luther King. I don't know who the guy is that's standing behind him looking at him, but that guy could change. Or that guy could stay the same, and Martin Luther King could be replaced by Dwight Eisenhower. And it wouldn't have to be a picture that actually occurred in history, although this did. I think this was the I Have a Dream speech or something like that. We could also see a picture of another television with a picture in it with a historical figure. And of course, that face could be anything. It actually could be your face as it looks now. Again, infinite. And lastly, we might see a picture of a future event that hasn't occurred yet. And that future event could be our funeral. Now, we said infinite, but the reality is, in the infinite image window, it's not infinite. It's what we call countably infinite. And of course, that came out in the thesis. If you're curious about this, you can go over to the library and read Proballa's thesis. But the infinite image window is basically a vision sort of into the ultimate end of the digital abstraction. And of course, I just chose these as examples. All right, let's talk about image processing in terms of computation. So we'll introduce some processing blocks. Here on the left, we have that scene from 2001, and we're going to go through a copying operation which causes that image to be copied. And in fact, when I made this slide, I took that picture and then I just cut and pasted it and copied it over to the other side. We could also define an inversion operator. And there we are going to take the original pixel voltage, that's the V, by the way. I'd like to tell you that. You take the original pixel voltage, each pixel separately, and our inverse is going to be defined as 1 minus whatever that voltage is. So we're going to take every pixel in the picture on the left and replace it with 1 minus the value at that pixel. Remember, the voltage that we selected was 0 to 1 volt. So if the pixel's a 1, it's going to change to a 0. And remember, If it's a 1, it was white. And if it's 0, it goes black. So if a pixel was white, we're going to make it black. If a pixel is black, we're going to make it white. If a pixel was 50% gray, it's not going to change. And that's going to give that negative effect to the picture, which you see on the right. Okay, why would we want to have these processing blocks? Why have these? Why have these blocks that do this processing? Why have I come up with this? Well, it gives us what's called modular design. And one of the goals of modular design is abstraction. Now, what does that mean, that abstraction? Well, first of all, it means, or the modular design, it means we're going to have rules that are simple enough for a 6-3 to follow. And a 6-3, this is the MIT thing. A 6-3 is a computer scientist at MIT. So I just put that little red line through there and put Lux on there. What's Lux? That's Lamar University Computer Science. So we're going to make this thing with rules that are simple enough for a computer scientist to follow. We want to have an understanding of behavior without knowing the implementation. So what does that mean? We want to know that we can make that negative image, but we don't want to get too involved with how it takes place in the electronics. Okay, remember, we're manipulating a voltage, and we've got circuits and electronics involved, but we want to know that it's doing that, but we don't want to worry about the details about it. We want to have a predictable composition of functions. Okay, a predictable composition of functions, which what that means is we want to be able to combine functions and know what kind of result we're going to have once we do that. We sort of want to have a tinker toy assembly. We want to be able to take these blocks and put them together. That's the composition. And or like Legos, that was the MIT thing, but in Lamar EE we have no Legos a lot. And we want guaranteed behavior. We want this to work under real world circumstances, which means that when we design our system with these blocks and put it all together and turn the key, hit the start button, we can predict, okay, this is what it's going to do. Okay, so let's build a system. So here we've got our input, which is our black and white picture, television picture, photograph, whatever, from 2001. And we're going to do a copy operations. We're going to copy the picture, then we're going to invert it, then we're going to copy it again, and then we're going to invert it. We're going to copy it again and invert it. We're going to copy it again and invert it. And what's the output going to be? Well, in theory, what did we do? Well, we just flipped it back and forth, didn't we? We just flipped it back and forth. But in reality, we might get a noisy image. Remember the infinite image window? The output may become corrupted because of these operations. And particularly that would happen, and it happened often in analog TV. Back in the day when broadcast TV was analog, this was not unusual to have a noisy image. So we have to ask, this block system that we created, why did it fail? Why did it not give us what we expected? Well, the copy operator doesn't work right. Something happened in when we copied it, didn't copy it. It copied some noise or something. The inversion operator doesn't work right. When we invert, it doesn't do it the way it's supposed to. The theory, maybe the theory's wrong. Maybe we're not correct in our assumption about how copy and invert work. The reality is imperfect. There's something wrong. We have a distorted reality. looking at the result. And lastly, maybe our system architecture stinks. Something wrong with it. And the answer to why our system failed is all of the above. Noise and inaccuracy. So it had a blurring, which is an inaccuracy, and we obviously had a noise, that noisiness overlaid, are inevitable. We can't reliably reproduce infinite information. So we must design our system to tolerate some amount of error if it is to process information reliably. So we have to be prepared for error. And of course, this is where the engineering comes in. Engineers were always having to deal with nature not wanting to do what we want her to do. So we have to build that in. So the key to system design. A system is a structure that is guaranteed to exhibit a specified behavior, assuming all of its components obey their specified behaviors. So what that means is that if each component, if invert inverts, and it inverts correctly, and copy copies and copies correctly, then when we combine invert and copy together in a system, then that system will behave correctly. How is this achieved? Well, contracts. What is a contract? When you sign a contract, you're agreeing to something. You're saying, I'll do this. I'm signing this. I'm going to pay you a rent check every month. I'm going to deliver something. There's all kinds of implied contracts. If you're interested in contracts, become an attorney. And by the way, I'll put a little plug in for the legal profession. One of my former students, he's been working as an engineer now for about 5 years, and he's decided he wants to go to law school. He'll become a patent attorney, so I've been writing some recommendation letters for him. Engineers make really, really good attorneys. And and I don't want you to get the wrong idea, but that's also how they can make a lot of money. Because they get paid well. But that said, a lot of work as well. Anyway, so every system component must have clear obligations and responsibilities. If these are maintained, we have every right to expect the system to behave as planned. If contracts are violated, all bets are off. So we're going to hold the system to a contract, and we're going to expect the system not to violate the contract, and if it doesn't, then it's going to perform correctly, and we're going to be happy. If it violates the contract, then it's not going to work right. Okay, so the digital panacea. Why digital? Why are we going to use digital? Well, the simple reason is because it keeps the contracts simple. You can have contracts with analog systems, and it's probably not going to be called that. But when you design in analog systems, you put in certain controls to make sure the analog signal stays within bounds and things like that. And that essentially is the contract. You're holding the analog system to a contract, but it is really, really hard to do. With digital, it's easy. The price we pay for this simplicity is robustness. So we have one block under contract, and it's going to produce a 0 or a 1 that goes to the next block under contract, and there's our contract. And we're going to expect that it gives us the right 0 or 1. But the problem is, the limitation is, the constraint, we only have one bit that's moving back and forth. So it's not very robust. We have to have a lot of parts to get lots of bits, which means we have lots of information being processed, which is what we want. But it's going to be complicated in that sense. The contract's simple, but the system's going to be complicated because of that one bit. However, at the end of the day, we get a guarantee of reliable processing over billions of bits. Billions of bits, we get reliable processing. I'm going to take a moment here and say, how much data is on your phone? 5 gigabits, 10 gigabits, something like that. All your images and photographs photos that you've got on your phone, all your text messages and things. When was the last time you saw a bit error? You didn't. Good luck finding one. So even with that huge number of bits, the probability of a bit error is near zero. Okay, and sort of to wrap this up, what if each bit, because we just said one of the things is robustness, could code 4 values instead of 2? Okay, well, that's what happens with messenger RNA. That's what happens in the coding scheme in biology. And so here, there's a 12-bit word, 1010101010, and versus the word that's on that messenger RNA, which is a 12 base word. So the UUUGAGGUGAAG, of course I just found that little graphic somewhere, and I probably should have made it simple. The bases, U, we're going to set 0, G1, A2, and C3, just to keep them straight. And if we look at that 12-bit word, it's going to be represented down there in the bottom, the 1 times 4 to the 8th, 2 times 4 to the 7th, 1 times 4 to the 6th, 1 times 4 to the 5th, and so on and so forth. Wait a minute. Let me back up on that. The binary word is the top one. And I'm going to put a graphic on it. The binary word is the 1 times 2 to the 11th, plus 1 times 2 to the 10th, etc., the way we've converted it all along. The bottom one is the RNA, which is the 1 times 4 to the 8th, the 2 times 4 to the 7th, and so on. That number is astronomically huge compared to the binary number because it's a more condensed code. And so my point is, if we were using a base 4 code instead of a base 2, we could code even more information in a compact space. And that's what DNA does. But why do we have to use computers? Why do we have to use binary? Remember the switch. The switch is either on or off. We don't have an electronic system, an electrical system, where the switch can be one of 4 values. DNA has that system with the molecules of the bases. Each of those is an organic molecule, guanine, adenine, and so on. And now we could do it electronically if we went to quantum computing, but again, we don't want to go there. We've got enough on our hands working with binary, but I wanted to point out it can be more complicated. It can be significantly more complicated. And of course, evolution has used a very, very, very powerful coding scheme in order to code the complexity of life. Sorry for stumbling around with that, but you get what I mean. All right, the digital abstraction. Despite some evidence to the contrary, the world is analog. So we're pretty much dealing with continuous signals. Analog in this context means relating to or using signals or information represented by a continuously variable physical quantity, such as spatial position or voltage. This comes out of Wiki. So there I've got a cannon, and the cannon is shooting a projectile, and that projectile, as it's moving through space, is represented by a changing physical quantity, which is the position that it's in space, the free space that it's in space. And we can analyze that mathematically on paper. But that movement of that projectile is an analog behavior. In EE, we talk about voltage, and we talk about current. There's a sinusoidal voltage, a sinusoidal current. You're going to deal with, you saw those in physics, you're going to deal with them in far greater detail when you get to circuits too, and electronics. And we can talk about power, because power is a relationship between voltage and current. We can also talk about electromagnetic fields. We see that down there in the lower left. Those are continuous quantities. And of course, you've looked at the magnetic field around a magnet. You probably did that in grade school with, what is that stuff called? Iron filings. And of course, the electric field, you can mess around with that using pith balls and other things. You probably did that in a physics lab. And there you see the electric field lines around a tower on the electrical grid. And so, I don't know if you're aware of this or not, but transmission lines that go, usually they're not around in cities. They're big transmission lines like that are out in the country, or they're along highways. But there's farmers that have put loops of wire on the ground underneath the transmission lines and stole power from the power company. And of course, that's illegal. Believe it or not, puts a drain on the system. And if they catch them doing that, there's some severe fines. So this is the analog world. The digital abstraction is sort of like a mind-body dualism. And that is a phrase that was coined by René Descartes. And this is an illustration that he drew back in whenever he lived. I don't remember. I pulled this off Wiki again. Descartes believed inputs are passed on by the sensory organs to the epiphysis in the brain, and from there to the immaterial spirit. So, of course, he did not have our technology, and he was sort of a philosopher scientist. But what he was saying is that we see things, and then they get represented somehow in the brain, where we have this sort of spiritual sense of what they are. In other words, how we interpret them in the brain is a spiritual thing, and as opposed to the reality of what they are. So here I've got this cup. It's physical, but in my mind's eye, I can close my eyes and still see the cup, and then I can move the cup around in my mind's eye. You get the idea. And that's sort of what the digital abstraction is like. But now we're abstracting into hardware, and we're in control. So we have the real world, all these different electronic and electrical things in our world, and we have the digital abstract world. And in that top diagram in the upper right, that is an analog signal. That's that dark signal changing in time, and let's call it a voltage. And then we're going to sample it So we're going to pick the values along certain discrete points along the signal, and then we can redraw the signal, and you see it has that blocky thing that's showing us sort of its digitization. And we can represent now those digital values in terms of bits. And then the middle diagram, we're going to get to that very, very soon. Those are CMOS transistors, MOSFETs, and we're going to use MOSFETs in order to do logic. The little table in the upper right of that middle diagram is what's called a truth table. And it's going to tell us what the digital values, the binary values of the output are based on the binary inputs. And then that symbol, I didn't realize, A was the transistors, B is the truth table, and C is the schematic or the symbol, and that's an inverter. Remember we had the inverter with the TV picture, the black and white picture? And so if the input is a 0, the output's a 1. If the input's a 1, the output's a 0. Those three things are really what we're going to spend all our time with. We're not going to spend a lot of time with A, with the transistors, so don't get panicky. You're going to spend a lot of time with transistors when you get to electronics. That's an implementation detail. Remember, we said we're not that interested in the implementation. We're interested in the mechanism or the final product. So we're going to spend a short time on the implementation and move quickly to the abstraction. And then that bottom diagram there on the right, that's just showing some software where you can manipulate the blocks. Those blocks do logic functions. And then you can look at the logic in time. You can see how the bits change in time. And we're going to be able to do those kinds of things with the simulations we have in labs. So I think you're going to find it quite interesting and fun. Okay, so the digital abstraction summary. The world we live in is analog and continuous for the most part. Okay, there are some examples of digital in the real world, but maybe I'll touch on those as we go along. I don't know. They're not important to this course. With sensing and analog conversions, we can replicate analog signals as digital. I already said we can use sensors, we can convert analog to digital, we can sample it, and once we get it into digital, then we can do all sorts of interesting manipulation. Digital signals can then be manipulated by software. We can also manipulate digital signals with hardware that we design. That is the basis of digital logic design. This is why we're here. The abstraction speaks to the fact that we now represent the behavior of a physical system as a digital one. And that's the digital abstraction. Thank you.